Continuing on page 63. All right, so number one, this protostar cannot be seen in visible light because it is enshrouded with a covering layer of gas and dust. Number two, radiation and outflowing gases eventually reach a level that halts the flow of infalling gases and dust. Now, this radiation is still, we're talking about infrared and lower frequencies, longer wavelengths. The mass accretion stops. And the protostar becomes pre-main sequence. And we'll get into what we mean by main sequence here in a bit. All right. At this point, it contracts far more slowly than the protostar. All right, so now we're getting a lot of pressure. And I have to pause here to emphasize what's going on here with pressure, especially with gases. When you compress a gas, that temperature is going to rise. And I've mentioned this before. Think of it like a bicycle pump. If you have ever used a bicycle pump and you pump up and down like that, you may have noticed that the barrel of that pump gets hot. Now, some of that heat is from the friction of the plunger. That is true. But the majority of the heat that you feel on the sides of that bicycle pump is because of the pressure itself. Pressure equals temperature. All right? And it's just to carry it through to another example. It's important to understand the difference between a gasoline engine and a diesel engine. The main difference between a gas engine and a diesel engine is that a gasoline engine has spark plugs and a diesel engine does not. A gasoline engine has spark plugs that will spark every time that cylinder is filled with vaporized gasoline to ignite that gasoline. In a diesel engine, you have what are called glow plugs. Those are used just to start the engine. But once that engine is started, once that diesel engine is started, those glow plugs shut off. Well, how do you ignite the fuel in a diesel engine? The pressure alone is enough to raise the temperature of that diesel fuel to an ignition temp. In a sense, a star is kind of like a diesel engine. You'll see. Now, the next piece here, there is a typo, so we need to take care of a typo here before we do anything else. Okay, it says finally at 10 to the 7th kelvins, and then in parentheses it says 100 million degrees Kelvin. Cross that out. That's not 100 million degrees Kelvin. That is 10 million degrees Kelvin. Okay. So this temp is a result of gravitational collapse and pressure. What happens at this point? Hydrogen fusion begins. All right. So that's 10 to the 7th kelvins, or 10 million kelvins. Again, let's go back to how we define temperature. It's the average kinetic energy of a sample of material. This primarily hydrogen gas has its individual particles moving at such a high speed, 10 to the 7th kelvins, 10 million kelvins. They're banging into each other, you know. So that's a lot of kinetic energy as these atoms bang into each other, and it gets to a point where now we have fusion, not fission, fusion. Fusion, in this case, 4 hydrogen atoms fuse to form 1 helium atom. It's really quite a process. Here's the rough and ready explanation for this. What happens, this is a street fighting description. What happens is that, well, if you have a helium atom, or a hydrogen atom rather, a hydrogen atom has 1 proton, 1 electron. All right. Now, if you have 4 of these, and we'll get into this in greater depth, but what happens is if you have 4 of these, that means you've got 4 protons, 4 electrons. 2 of those protons plus 2 of those electrons will form 2 neutrons. And so now what you got left are 2 protons, 2 electrons, and that is a helium atom. A helium atom has 2 protons, 2 neutrons in its nucleus, plus 2 electrons. All right. And again, this is the rough and ready description of what's going on here, but we'll get into greater depth. But just understand that for now. And also remember that 10 million kelvins is the minimum temp you got to have to trigger hydrogen fusion. 10 million kelvins to trigger hydrogen fusion. Very important. All right. Now, at this point, contraction is halted by the outward pressure due to fusion. The outer shell of gas and dust dissipates and the star becomes visible. Overall, the more massive the pre-main sequence star, the sooner the fusion process begins, which would kind of make sense. If you have more mass, you have more gravity. If you have more gravity, then you have more pressure. And the quicker you get to that point of pressure that gets us to 10 million kelvins, the quicker we're going to get fusion. And the quicker you're going to get a star. All right, so for example, if you have a pre-main sequence star that starts at 5 solar masses, this process will take less than 1 million years to begin fusion. If, on the other hand, you have 1 solar mass, like us, this process from pre-main sequence to fusion can take tens of millions of years. But that's the basic process. Starting with a nebula, starting with giant molecular clouds, and then we get to Bach globules, dense cores, get down in temperature to the Jeans instability, 10 kelvins, and then the accretion process begins, and eventually we get to this point where enough material has accreted, we build up pressure, that pressure equals temperature, that temperature gets up to 10 million kelvins, triggers the fusion process, and yes, now we have a star. That's how it's done.